Welcome back to the course on nanostructured materials, synthesis, properties, self-assembly and applications. This is today we are going to have the second lecture of module 2. In module 1 we gave 2 introductory lectures, and in module 2 in the first lecture we started on synthetic methodologies, and we would be continuing on that for 12 lectures. And in the first lecture of module 2 we introduced the sol gel methodology, and in the sol gel methodology we showed how you can prepare nanostructured materials starting from a sol and how to make a gel, then what is an aerogel, what is a zero gel, and these kind of concepts we discussed in lecture 1 of module 2. We will be continuing on the sol gel method in this lecture also. So, once you get the gels, you have to dry the gels because the solvent is inside the pores. Although it is more or less like a solid and it is not flowing, but you have to take out the solvent from the pores of the gels. Now, if you take out the liquid from the pores and make a dried gel, then it is called a zero gel, and there are different processes by which you can dry these gels. For example, you can get a cryogel which results from freeze drying process. You can get an aerogel from a supercritical drying process which is normally performed inside an autoclave. Zero gel is the result of gentle drying at temperature close to room temperature and atmospheric pressure. Now, in this sol gel method, what are the starting materials or the precursors? We use metal alkoxides or typically metal chlorides, since they react with water readily. Example TEOS, which is a very common starting material, which is tetraethoxysilane. So, if silane is 4 hydrogens are connected to silicon, and if you remove those 4 hydrogens with 4 alkoxy groups, here ethoxy groups, then it is a tetraethoxysilane, and this is one of the most common starting materials in sol gel synthesis of silica or silica based particles, and this is TEOS. So, you can start with TEOS, then you can get a colloid with a broad range of solid particles which is dispersed in a liquid, and then you sediment and centrifuge it and then dry, and which will lead to hydrolysis and condensation. So, that is the typical process from which you get a nanostructured material starting from metal alkoxides or metal chlorides, then reacting with water and then drying it to get the final nanostructured materials. The 2 processes very important is hydrolysis and condensation. This can be shown as various stages, for example, in the polymeric citrate method, where we are starting we are going to make a nanostructured material through a route which involves polymerization, and hence it is called a polymeric method. It is called the citrate method, polymeric citrate method, because we are going to use citric acid which will help in polymerizing. So, what you see here is you see there is a magnetic stirrer, and on that magnetic stirrer you have a beaker, you can have a conical flask, and there is a magnetic pellet here, and once you turn on this instrument, this magnetic stirrer, then it will stir the solutions, and you can see that there is a tube in which some liquid is there, and there is a rubber tube through which a gas is passed, which is typically nitrogen, which goes into this reaction vessel. And so, what you are doing is you are stirring in a absence of air or in the presence of nitrogen, and you start with say ethylene glycol and titanium isopropoxide as your starting materials, and then you can see slowly after some time a white precipitate when you add citric acid, and this is also being heated at some temperature like 60 degrees or so. So, this white precipitate will dissolve after some time and you will get a clear sol. So, you have added an alkoxide which is titanium isopropoxide, you have added ethylene glycol and you have added citric acid, and so you dissolve it at around 60 degrees to get a clear sol, and then you allow it to cool and settle down, and slowly this will become more viscous because of condensation between citric acid and ethylene glycol, and this will become darker and then it will become black, that is the gel has formed, and when you dry it little bit say around 135 degree centigrade, you get this black mass of a polymeric gel, and then you heat it at higher temperature and then you get the oxide, nanostructured oxide of titania which you wanted. Now, this process is typically what is called a polymeric citrate method. It is a sol gel method which involves polymerization using citric acid and ethylene glycol. So, you can follow either the colloidal route or the polymeric route to do this sol gel chemistry. So, typically if you follow the colloidal route, you get colloidal sol and then a colloidal gel, and you can dry it to get a hybrid organic inorganic membrane, or you can sinter it at higher temperature to get a pure inorganic compound like TiO2 or zirconia, or a oxide like barium titanium oxide through this route. The other way is the polymeric route, where you add ethylene glycol or citric acid, and then you get the sol like we showed, and then a polymeric gel which is much darker in color, and then dry it to get the organic inorganic membrane, or you heat it higher when all the organic stuff will be burnt away, leaving behind only the inorganic membrane. So, you can get these final products either through the colloidal route or through the polymeric route. Now, this kind of sol gel chemistry is used in making membranes, and one example as you can see here, this is a multi-layer ceramic membrane which is made up of a macroporous support. So, what you see is 3 layers 1, 2, 3, in which you have a macroporous layer, a mesoporous layer and a microporous layer. Okay. And how you define this microporous, mesoporous or macroporous is by the pore size. Each of these membranes which you are making through sol gel chemistry or colloidal processing. Normally sol gel chemistry gives you mesoporous or microporous layers. Now, the definition of a microporous layer is that the pore diameter it should be less than 2 nanometers. Then it is called a microporous solid. If the pore diameter is between 2 to 50 nanometers, then these are called mesoporous structures, and if the pore diameter is much more than 50 nanometers, then these are called macroporous structures. So, together you see you can have a membrane which is made of all the 3 pore sizes. So, here the pores are very small because it is microporous and it is less than 2 nanometers. Here it is mesoporous. So, it is between 2 nanometers and 50 nanometers, and this is the macroporous layer which has pore diameters of around 50 nanometers or more. Now, these can be used for a separation of various materials, and you can do filtration through these multi-layer ceramic membranes, and these have lot of applications in industry and elsewhere. So, you can use sol gel chemistry for the synthesis of micro and mesoporous membrane systems. Now, as you see that you can get these kind of microporous and mesoporous systems using sol gel chemistry, but you can do that using colloidal routes or the polymeric precursor route. So, in the colloidal route you start with metal oxide and the solvent is alcohol, and you do precipitation and in this colloidal route the alkoxide concentration is very less compared to the water, whereas in the polymeric route you do this kind of reaction in a system where the alkoxide is much larger than the amount of water, nearly 2 to 4 times larger than the quantity of water. Here in the colloidal route, the concentration of alkoxide is much less than that in water. Then in this colloidal route you get colloids in an aqueous medium which are separated due to repulsion between the particles, and that is how agglomeration is prevented. In the polymeric route you get an inorganic polymer, like from the condensation of ethylene glycol and citric acid you get a polymer, and the agglomeration is prevented by the small size of these agglomerates. In the colloidal route you get a gel as a result of electrostatic effects, as you see that the particles are prevented by the particle repulsion and there are some charges on the surfaces, and you get a gel as a result of electrostatic effects. In the polymeric route you get the gel as a result of further polymerization. In most cases in the colloidal route you get crystalline particles, that means the particles in which the atoms are regularly arranged over a long range. So, they are called crystalline, whereas in the polymeric precursor route the gel which you form as a result of polymerization leads to amorphous structures, and most of the time in the polymeric route you get microporous systems. So, there are some little differences between the colloidal route and the polymeric route for making nanostructured materials through these sol gel based methods. Now, this is a typical example of synthesis of alumina nanoparticles using the sol gel method. So, what you have here is the alkoxide here that you choose is aluminum alkoxide. It is tri aluminum secondary butoxide, and you hydrolyze it with water. So, there is hydrolysis and you keep the temperature around 90 degrees Celsius. So, there is hydrolysis and then polycondensation, and you get what is gamma alpha oxyhydroxide, which is commonly called boehmite, and this is a precipitate, and then you heat it to remove the alcohol. You add some nitric acid to maintain stabilization, and then you heat it at 80 degrees for the peptizing action to take place, which will give you a stable sol. And then after gelation, you calcine them and you get mesoporous particles of between 2 to 50 nanometers, and typically if the temperature of this calcination is kept around 400 degrees Celsius, you get pore diameters of around 3 nanometers, and if you heat it at higher temperature like 800 degrees centigrade, then you get particles which are mesoporous and have average pore diameter of around 5 nanometers, and these are gamma alumina. So, you start with the aluminum alkoxide and you end up with gamma alumina nanostructured particles and with porosity of in the range of 3 to 5 nanometers, and so you get mesoporous alumina using this sol gel synthesis. This is a similar example, except now instead of alumina you are going to make titania. Titania is TiO2, and TiO2 you have to if you have to prepare using the sol gel synthesis, you start with titanium isopropoxide and you take this titanium isopropoxide in isopropanol, that is an alcohol. So, you dissolve this titanium isopropoxide in isopropanol and add another solution containing isopropanol and water, and then hydrolysis and polycondensation occur, which then gives you some precipitate which you filter and wash to remove the alcohol. And similarly to the synthesis of alumina, you add nitric acid for stabilization and then peptization at 80 degrees centigrade to get a stable sol, and then it undergoes gelation and further calcination at different temperatures gives particles of different size. So, here the particle size varies from 20 nanometer to 50 nanometer if you depending on the temperature at which you calcine. So, if you are calcining at 300 degrees centigrade, you get particles whose size or average diameter is 20 nanometers, and if you look at its crystal structure using powder X-ray diffraction, then you will find that this TiO2 has a structure which is called the anatase form of TiO2. TiO2 has 3 different forms. One is anatase, another is rutile, and the third one is bruchite. So, in this methodology, if you heat or calcine at 300 degrees centigrade, you get anatase form of TiO2, but if you heat at 600 degrees, not only the particle size increases, it goes to 50 nanometers, you also change the structure of TiO2, you now get the rutile form of TiO2. So, both anatase and rutile structures have the same composition of TiO2, but they have different structures, and depending on your temperature of calcination you can get either anatase or rutile. So, this is a typical synthesis of one of the most important nanostructured materials, which is TiO2, which is used for many applications using the sol gel method, using titanium alkoxides and hydrolysis and polycondensation, and then calcination to get the final inorganic oxide, which is titanium dioxide or TiO2 in two different forms at two different temperatures, and of course, the particle size changes. At low temperature you always get smaller size particles, at high temperatures you get higher sized particles. So, this is again a sol gel example. So, we looked at alumina synthesis and then titania synthesis, and then this is a example of silica, which is again a very important nanostructured material for many applications. So, again starting from silicon alkoxide with different alkoxy group, you can vary them, you can take ethoxy group, propoxy group, butoxy groups, you can vary them, and once you react these alkoxides of silicon with ammonia and in some alcohol, and then you hydrolyze it, you add water under constant stirring, you can get silica, and you can get very nice spheres of silica which are of the order of few nanometers, say 10-20 nanometers. So, we discussed three examples of some of the most important nanostructured materials used in large tons of kilograms are used, thousands of tons of kilograms of these materials of titania, alumina and silica are used in industry. This is a synthesis of another very important material. It is called PZT, where P stands for lead, Z for zirconium and T for titanium. So, this is an oxide of lead, zirconium and titanium, and it is a very important dielectric oxide. It is used in capacitors and many other devices, for example, as transducers, etc. So, this is a material which involves lead, zirconium and titanium. So, how you obtain this material using the sol gel process is you start with an titanium and zirconium alkoxides. So, you have this tetra propyl alkoxide of titanium and of zirconium, and you take an alcohol, dissolve them in alcohol. So, this is propyl alcohol or propanol, and then you add acetyl acetone, a ligand, and simultaneously you add lead acetate hydrated. So, you dissolve it in water and add the solution of lead acetate. So, basically it will have lead ions in solution. So, you have titanium ions, zirconium ions through these alkoxides in solution in isopropanol, and you have lead ions in solution, and you mix this, and this liquid reaction mixture will be having all the three metal ions, lead, titanium and zirconium, in the right proportion that you want, and then you remove all the volatile, that is the acetyl acetone and water and alcohol, and you are left with a solid lead, zirconium, titanium oxide precursor, and then you can dissolve in alcohol and you can coat it on a substrate. And if you want to get the powder, you heat it or anneal it between 575 to 700 degree centigrade, and then you can get a polycrystalline film or a nanocrystalline film. So, this is a process using sol gel chemistry to get a polycrystalline PZT film. If you need a powder, then you just dry it and you do not have to coat it, but after this precursor you can dissolve this solid precursor will be, you can heat it at high temperatures to get the oxide powder. However, to coat it you have to dissolve in alcohol and then make a coating sol, and then after coating you have to anneal the film for further applications. So, this is another example now of making a very important material, which is a p doped indium tin oxide. And indium tin oxide is a very important semiconducting material and is used in many applications. So, as a substrate, ITO is used as a substrate, and this is prepared using condensation of a stoichiometric mixture of an alkoxide of indium. Here it is shown as tributoxy indium, and you add to that tetrabutoxy tin. So, you have indium and tin in a ratio of 10:2, and then you heat it so that you get the gel, and this will lead to p doped indium tin oxide. So, that is the reaction shown here, where you have the tributoxy indium reacting with the tetrabutoxy tin to give you indium tin oxide, which is a very important material. Now, this polymer route of making nanostructured materials through the sol gel polymerization route is again shown here, where the two important steps are again shown, where you have the hydrolysis step. So, this is alkoxysilane, tetraalkoxysilane, and on hydrolysis it loses alcohol, which you have to remove, and then you get this hydroxyl group in here, right, and under you again further hydrolyze till you get all these hydroxyl groups, which can then undergo polymerization, condensation, polymerization, and yield to you finally these SiO-Si linked structures. So, this is in short, you have hydrolysis and then you have alcohol condensation. So, this is the reverse of this is esterification, and the reverse of this alcohol condensation is alcoholysis. So, in hydrolysis reactions you replace an alkoxy group with the hydroxyl group, and in the condensation reactions you involve the silanol groups, the SiOH groups react or condense to form SiO-Si bonds, which are called siloxane bonds, and you get byproducts like alcohol and water. So, this is to summarize these two important reactions which always take place in sol gel chemistry. Now, how do you adjust the processing parameters in a typical sol gel method? So, how do you control a sol gel process? There are various controls. You have some internal parameters and you have some external parameters. So, the internal parameters which affect a sol gel reaction is basically the nature of the metal atom and the alkyl or oxide groups present on it. The second thing which depends internally is the structure of the metal precursor. The factors which you can change from outside is like water, or the amount of alkoxide that you take, the amount of catalyst that you add, whether you do acid catalysis or basic catalysis. That means, whether it is acid hydrolysis, the reaction which you catalyze is the hydrolysis or condensation of reactions. So, that these are affected by the conditions present. The acidic conditions or basic conditions will determine the extent of hydrolysis and condensation and the rates at which these hydrolysis and condensation takes place. And so, this can be controlled using the amount of acid or base that you add. Further, you can vary the concentration of the solvent, you can vary the concentration of the precursor. Also, the nature of solvent you can change, and finally, the temperature. So, all these parameters will affect the rate of this sol gel process, and on that will depend on your final product. So, again to tell you the mechanism of hydrolysis and condensation in the polymeric route, you have the hydrolysis process. If it is acid hydrolyzed, then you in the presence of water, this proton will first protonate this oxygen, and you get this, and then it removes this alcohol ROH group, and you get this silanol group introduced. So, this is a typical acid hydrolysis, which is guided by the initial attack by the proton on this oxygen. Now, if you do further on this product, so you have one alcoholic group, you can continue this further and replace the other alkoxide groups with alcoholic groups. You can also have a process like this, where you have a water molecule which is reacting with this alkoxide, and then giving you this product, and then this ROH group leaves to give you this. Now, if it is base catalyzed, then you have the OH minus group, which will react and will attach on the silicon and making this oxygen negative, and then you get this SiO trialkoxy group, and with alcohol group here, because one of this alkoxy group is which is a leaving group, it will leave, and so in total one SiOH bond is formed, the silanol bond is formed, and one OR group is eliminated. So, this OR group of course reacts with water and forms an alcohol group. Now, this is the reaction mechanism for hydrolysis in the presence of acid or in the presence of base. Similarly, you can have condensation in the presence of acid. So, you have two of these silanol groups, and then they form a SiO-Si linkage in the presence of this proton, which is protonating here on this oxygen, and giving you a condensed product in which a SiO-Si bond is formed. If you do a base condensation, then you have hydroxyl group here to react, and one water molecule leaves, and you have this O minus group, and this O minus group then reacts with another molecule of this alkoxysilane, and you have this SiO-Si bond with a loss of OH minus group. So, you can have hydrolysis under acidic or basic conditions. Similarly, you can have condensation in acidic or basic medium. Okay. So, this is probably another clearer picture of the mechanism of acid catalyzed hydrolysis. So, you can see this we described in the previous slide too. So, you have first protonation, and then this water molecule reacts because now there is more this electron density on oxygen here can react on this silicon, and then you get a delta positive charge on this water molecule, and this delta positive charge remains here, and so one alcohol group will leave, creating one new SiOH linkage. These acid catalyzed reactions normally take place at pH of less than 2.2, and it has a fast protonation step, and the silicon becomes electrophilic after the protonation, and therefore is more susceptible to attack by water, and the protonation becomes slower when more hydroxyl groups are present. Now, in basic conditions, the OH minus group attacks the silane tetra alkoxide silane, and you get this kind of a OH delta minus charge here, and this also gets a OR delta minus charge, and then this OR minus leaves, and you are left with a new silicon hydroxyl linkage, and this base catalyzed reaction normally takes place at pH greater than 2.2, and it takes place via dissociation of water and hydroxyl ions, and the attack of these hydroxyl ions on silicon. So, that is how the base catalyzed hydrolysis takes place. When you have condensation of alkoxides, this is the second step. After hydrolysis you have condensation, and when you have condensation of alkoxides under acidic conditions, then you are going to create this SiO-Si linkage, and this will give you a linear kind of polymer. So, acid catalyzed condensation always leads you to linear polymers, and you can see these chains of linear polymers based on condensation of alkoxides. This is a scanning electron microscope picture of these kind of linear polymers. So, this reaction occurs through the protonated silanol species Si-HOR plus and results in linear polymers. This is under acidic conditions. Now, what happens in basic conditions is that this condensation normally leads to branched compounds. So, this kind of branched compounds you can see, because this will bind here to form a silicon oxygen silicon bond, and this silicon oxygen silicon bond will give rise to this branching. So, base catalyzed condensation always leads to branched polymers, whereas acid condensation, acid catalyzed condensation leads to linear polymers. The base condensation will take place through the attack of a nucleophilic deprotonated silanol, and which takes place on a neutral silicate species, which is shown here, and results in more branched polymers. So, then the kind of morphology means the shape of the particles or the polymers that you get under acid or basic conditions are different depending on where you are close to the gel point or far from the gel point, etc., and also whether you are using acidic conditions or basic conditions. So, if under acidic conditions you are doing this reaction and you are far from the gel point, then you get this kind of linear polymers with very less branching and which are very loose. However, if you use acidic conditions and you are near the gel point, then you get entangled linear molecules. So, a lot of linear molecules which are kind of crisscrossing themselves. This is when you are close to the gel point and you are using acidic conditions. So, here also you see long chains like you see in this case, but there are more chains and they are more crossing each other. When you are at the gel point, we will have additional cross links at the junctions. So, wherever they meet, you will have additional linkages if you are at the gel point. Now, if you look under basic conditions and you are very far from the gel point, then you see this kind of branched cluster kind of things. However, when you are close to the gel point, then you will see lot of growth and additions and lot of branching of course. Whereas, if you are at the gel point, you get nearly a connected structure, however, with lot of branching, but the whole thing gets interconnected when you are in the gel point. This is in the basic conditions. So, if you compare the acidic and the basic condensation, you see that under the acidic conditions you get more porous or more sparsely arranged chains, whereas in basic conditions you get more close knit chains or clusters which have small lengths. However, when they get interconnected, especially at the gel point, these small clusters are all networked together. So, these are different type of morphologies or structures which you can observe at acidic and basic conditions. So, the sol gel derived silicon oxide networks under acid and basic conditions yield linear or randomly branched polymers, and as you increase or come close to the gel point, they will entangle and form additional branches. On the other hand, if you use this was using acid catalyzed reactions. When you use base catalyzed conditions, they yield highly branched clusters which do not interpenetrate prior to gelation and thus behave as discrete clusters. So, this is when gelation is taken place. Before gelation, they exist as independent clusters which are highly branched. Now, what are the advantages of the sol gel technique? So, by the sol gel technique, you can make many different types of nanostructured materials. As you saw that we looked at examples of gamma alumina, anatase and rutile form of TiO2, or a dielectric ceramic like PZT, lead zirconium titanate. So, several different materials can be obtained in the nanostructured form using the sol gel technique. The advantages of using this technique are as follows. You have control of the product morphology. So, you have controlled on you can control the porosity, the connectivity, the primary particle size during the processing of the material using the sol gel technique. You can change the amount of water, the amount of alcohol, the amount of citric acid if you are using a polymer method. So, all that comes in the processing, and there are several ways of controlling the product morphology. Sol gel method is cheap and the temperatures at which you are operating are not very high. Then you can easily shape the material once it is formed as a powder, or you can make a film. Those powders can be compressed and make into monoliths. You can get very pure monophasic compounds, that means the stoichiometry of the ions can be maintained by proper control. So, homogeneous compounds or pure phases can be obtained. You can get very small particle sizes. If you want, you can get 2, 3, 5, 20, 30 nanometer particles. So, you can vary the particle size by varying the conditions of the sol gel process. Then it is a relatively complex method. Of course, you have to know some chemistry and you must know how to handle these chemicals. You must know when to avoid air, like you pass nitrogen as we showed when you are doing a citrate gel method synthesis. You stir the solution properly, you have to make a clear transparent sol which will settle to a gel. So, some good handling and chemistry is required to use the sol gel technique to the full potential. Continuing on the advantages of the sol gel technique, you can not only get powders, you can get very thin film of these oxides. On various substrates you can coat them. Since you get a transparent sol, at that stage you can coat that sol on various substrates like glass or quartz or silicon, and then you can dry them to make thin films of oxides. Those thin films, of course, once you coat with the sol, have to be heated to get more mechanically stable films or ceramic films on the substrates. Another advantage is the uniform distribution of the components. So, if you have lead, zirconium and titanium, 3 different metal ions in an oxide. So, using the sol you can get very homogeneous solution, because it is now not a solid, and then this homogeneous sol, not a solution, it is a homogeneous sol, can give rise to very good quality of coatings or powders as you wish. So, it is a better alternative approach to conventional production of glasses. So, many times you make glasses using very high temperatures. Glasses are also called amorphous solids. So, many times they are obtained using very high temperatures and then they are cooled very rapidly to obtain glasses. However, with the sol gel technique, it is very easy to get glasses or amorphous solids at much lower temperatures. You can control the addition of each dopant during the ceramic processing. So, you can really make compounds with several different ions using the sol gel process. The sol gel material can be obtained in various forms, in bulk materials, as thin films and as nano powders. So, all these are various advantages of the sol gel technique. Now, these sol gel produced powders or coatings have several applications, and as you see, this is an optical coating. So, this is a glass on which there is a coating using a sol which is converted into a gel. So, when it is a sol, it is this glass plate is dipped in a solution in that sol which is kept in a vessel, and then it is taken out of that vessel, and that coating here it is a transparent coating, and hence you can see through, but it may have other properties depending on what was there in the sol. So, you can have different properties of this glass by the coating of the material using the sol gel process. So, if you coat with silica, you can get some properties. If you coat with titania, of some properties. Also, what is the size of the nanoparticles in this sol gel derived titania or zirconia film, which is on top of the glass, will determine its properties. For example, the optical properties of this glass can be controlled by the kind of material you coat on that using the sol gel process. So, if you coat a particular type of material, maybe it will cut down UV radiation. So, only a visible range of radiation which is not harmful can pass through this glass, or you can have glasses which will be transparent to some wavelength other than what is visible, and for some specific applications maybe you need only IR wavelength of light to pass through, then it will require a coating of a different kind than one which passes through only visible. So, these are applications for optical coatings. Then you can have similar optical coatings on the car windows. You can have dense ceramics. So, this is a dense ceramic which is a made up of a nanocrystalline or polycrystalline powder which was obtained by the sol gel method, and then it was compacted and sintered to get this kind of a disc form, which may have properties depending on what is the compound by which you have made this disc. Now, you can make thin films on top of some substrate like shown here using sol gel chemistry. You can have powders. So, the ceramics you can put it in a mold and get powder rods like this which have certain applications. Then you can just have a layer of uniform particles on a surface made through the sol gel process. So, with all this, what I wanted to discuss with you was the first method in the bottom up approach, which is the sol gel method, which we have discussed so far, and we will be discussing other methods, chemical routes or low temperature routes as they call, which together form the bottom up approach to nanostructured materials. So, today we are finishing the second lecture of module 2, and we have basically discussed in these two lectures the chemistry and the processing and applications of a methodology which is the sol gel process to make nanostructured materials which may be in powder form, in thin film form, or as fibers or discs. So, many shapes and sizes you can make nanostructured materials using the sol gel process. So, you must remember that the sol gel process is a low temperature process which has wide applications, and some of the general oxides which is used in industry in very large amounts, as I said, thousands of tons, maybe millions of tons, some of them. We discussed alumina, gamma alumina, titanium dioxide or anatase form and rutile form, and lead zirconate titanate. These are some very few examples. There are thousands of other examples of making materials using the sol gel process. So, in the next two lectures, then we will discuss another low temperature method, another bottom up approach to make nanostructured materials, and that is a method using microemulsions. So, we will discuss what are microemulsions and how they are useful in making nanomaterials with controlled size, shape, and hence by which we can control the properties of those nanostructured materials. So, goodbye for now, and then we will meet for the next lecture, which will be the third lecture of module 2. Thank you very much and see you again.